Welcome, fellow chemists, to a new and exciting chapter on stoichiometry. Stoichiometry is kind of a strange word, and we've been using this all our lives, but not necessarily in chemistry. In cooking, in cars, and pretty much everything, we look at a recipe for making something. For example, a cake. On this recipe, it says that I need a half a cup of butter, 2 cups of sugar, 4 egg yolks, etc., to make a simple butter cake, which is quite delicious. Now, if I wanted to have 2 cakes, of course, I would have to double how much butter and sugar and egg yolks, etc. And of course, if I wanted only half of a cake, then I would split everything in half. And stoichiometry is very similar to this, except we can go, instead of cups and egg yolks and cups of sugar, we would actually do moles, and we could even change those to grams. So when we look at balanced equations, they're very similar to recipes. So stoichiometry involves the mass relationships between reactants and products. And here we have a balanced equation. We have ammonia and oxygen. This looks like a very simple reaction, and we have the coefficients highlighted. So we see over here we have 4 parts of ammonia and 5 parts of oxygen will produce us 4 of these and 6 of these. Now we could say 4 moles and 5 moles. We could use those numbers. We could change those to cups or a lot of different measurements. But in chemistry, of course, we're going to use moles, and then using the periodic table, we could also change those to grams. Now, taking a closer look at that equation, we can also come up with mole ratios. So taking those coefficients from the very front, we can have a ratio of 4 to 6 for ammonia to water. Or we can have a 5 to 4 ratio for the oxygen to nitrogen monoxide. So looking at ratios is going to tell us how much of one thing will produce a certain amount of the other. So using this balanced equation, we can answer a simple question. It says, how many moles of H2O will be formed from 5.6 moles of NH3? Well, like we've always done in previous chapters, we write down the number that we're starting with, which is 5.6 moles of NH3. And then we would draw our chart, and then we would use what we're going to call our magic step. So here I'm going to highlight our magic step. This is where we use the coefficients, and this is the only place that we can use coefficients. It's magic. We went from ammonia, and suddenly we have changed it to H2O. The magic step, the numbers came from these coefficients. We have 6 parts water, and we have 4 parts ammonia. So this is the only time that we use a number other than 1 for moles. Again, it's called the magic step. So, of course, that means to get our answer, we would take the 5.6 times 6 divided by 4. And so really the only new thing that we're doing in this chapter is that magic step. It's very strange to see moles on top of moles, but that is so that we can change from one chemical to the other. So looking at this balanced equation, it's kind of neat. We can change from NH3 to O2, or we can change H2O to NO. We can do any possible combination of one chemical to the other, so we can find out what 6 moles of water would make, or 5 moles of oxygen would make, all through the magic of the magical step. So using that same balanced equation, we can do another problem where we're going from moles to grams. And it's really just adding one extra step to the whole equation. So what I would write down here is the 12.5 moles of NH3. And then I'm going to draw my little chart there. Now I'm automatically going to put moles of NH3 down here. And instead of changing it to grams of something, I'm wanting to change it to H2O. Now I can only change from one chemical to the next using the magical step. And here's where I put my numbers, my coefficients from the balanced equation. So I'm going to put a 6 right here for the H2O, and I'm going to put a 4 down here for my NH3. So if I just did this calculation right here, I would find out how many moles of water, but the question's asking for how many grams of water. So we've done this in previous chapters. This one last step, we would put mole of H2O down here, and we're always going to use 1 unless it's our magical step that we used last time. And anytime we have mole on one side of the line, we're going to put grams on the other side of the line. And where do we get grams from? That's right, we get grams from the periodic table. Oxygen weighs 16, and 2 hydrogens makes 18. So we would be done when we multiplied 12.5 times 6 times 18 divided by 4 to get our answer. This, of course, brings us to our worst possible situation, going from grams of one all the way to grams of the other. So, like usual, we're going to write down the number that they gave us in the problem, which is 54.9 grams of NH3, ammonia. We're going to draw a line, it's going to be a long line. So I'm going to put grams of NH3 down here and moles of NH3 up here. This is why it's very important to write NH3 and not just grams and moles. We're going to use 1 for mole. We're not doing any magic yet. And grams we're going to get from the periodic table. Nitrogen weighs 14, and 3 hydrogens each weigh 1 to give us a total of 17. So get rid of that. And we now have moles of NH3. Of course, we want to actually change it to water, H2O. So this is exciting. We're going to do our magic step. So we'd have moles NH3 here and moles of H2O up here. And our coefficients from the balanced equation at the very top, we got our 6 that we're going to use down here, and for our NH3 we're going to put our 4 here. So that was our magic, very magic step. Hopefully you felt the magic. And it's asking us to go to grams. So we actually have to go to one more step. We're going to put moles of H2O down here to cancel it. And it's tempting to use the magic, but we can only use 1. And on the other side of moles, we're always going to use grams. And just like the last problem, we get grams from the periodic table to get our answer. And if you multiply the top and divide the bottom, you would find that you would get 87.1 grams of H2O. It's a long problem. Okay, so looking back at this, we're doing nothing different this chapter except for the magic step. We're still getting grams from the periodic table. We're still using 1 for mole. The only exception is in our magic step where we're changing from one chemical to the next, and that's when we can use our coefficients from the balanced equation. So hopefully you can see that chemistry is very similar to cooking. In cooking we have a balanced recipe, and we could change the butter into grams and the sugar into grams, and we can even play around with this recipe and make it look like a stoichiometry problem with balanced equations. But hopefully you understand a little bit more of stoichiometry. We do have one more section after this on limiting an excess reactant, so you may want to watch that. But if you understand this, great. If not, replay it, or you may go on YouTube and find a few other people that are showing stoichiometry. There are many, many ways to teach it, and sometimes those little tiny keywords make all the difference in understanding it. So thank you for watching, and enjoy the next video.